Good morning, Calc 2 students. I have a little bit of information for you. Thanks for taking the exam yesterday. It went off pretty much without a hitch. As far as I could tell, I will begin grading them and giving you feedback on those today. And it's the first exam I've graded on Foxtail, so I'm not sure how fast. And you know I like to have exams back quick, so we'll see how that goes. But I want to talk about Section 3 today. Before you watch this video, you should have watched the calculus professor's video on Section 3. The title of the section is Taylor series. They're a special kind of power series we want to look at there. And I've watched the calculus professor's video, and there are just a few things I'd like to add to his presentation. So in particular, now remember, you've already watched his video, so I don't need to dig into the detail. I just want to talk about some of the consequences. So on the board here, you can see what a Taylor series. I want to talk about when it actually converges to the function. The calculus professor didn't say anything about that. He just kind of assumed it always did, and some do, some don't. So we need to be a little bit more careful. So what is true, a Taylor series and a Maclaurin series, they are power series, just like we learned about in Section 2. Therefore, they have a radius of convergence and an interval of convergence. And once we figure out what those coefficients are, explained very well in the calculus professor's video, then we need to take it one step further and find out what is the radius of convergence. That is, what are the x values for which what we just found out, the Taylor/Maclaurin series, for where it really makes sense. Okay, and so because they are power series, we know how to find, because we did Section 2, we know how to find the interval of convergence. And like I say, we use techniques primarily. I think the examples I'm going to give, all we will use is the ratio test for absolute convergence. And if we do it, then we get these results. In the video, he does the derivation, all of them, for the sine of x, and this is the series that you get. Sine of x hits only those odd powers because every other derivative is 0, evaluated at 0. Notice all of these, the first two series are evaluated centered at 0, and this one is a little bit different. Okay? So once we find the series, notice it's a power series. We need to find the radius of convergence. And those are the values of x for which this is actually true. That polynomial type thing converges to this transcendental function. So I'm not going to do the details here. There's a question on the exam very much like this, but the ratio test, it just works perfectly. I mean, you probably by now you figured out that when factorials are involved, the very first test you should think about is the ratio test. And it works perfectly. The limit is 0, which means it doesn't depend on x. And since 0 is less than 1, it converges for all x values. Okay, super powerful result. These are the same function. This is a periodic function. Its period is 2 pi. We know because it's exactly the same function as that. Okay, now he didn't do maybe the most important. He didn't choose it as an example, but I'm going to talk about it here. The most important Maclaurin series, probably in my experience, is the one for e to the x. And here's what we get. Now think about it for a minute. To find the Maclaurin series, we need to take derivatives. Well, all of the derivatives are e to the x or e to the x. If I center it at 0 for the Maclaurin series, when I plug in 0, I get 1 every single time. So it's like we're plugging in a 1 right here to be the value of the derivative. And then when we find the coefficients, remember, as explained in the other video, we always divide by the corresponding factorial. So you can see easily that's the series that we get. And again, use the ratio test. You're going to get 0 just like you did here. And so it also converges for all real numbers. In just a minute, we'll do an exercise with our calculators to illustrate that. Finally, if you look at the first two examples, it appears that maybe the calculus professor didn't really need to talk about interval of convergence, radius of convergence, because they converge everywhere. But when you look at his another example, I think it's example 4 in the playlist, he looks at the function 1 over x, And here is the series he derives. And now all of a sudden, this series does not converge for all x. If you use the ratio test, you could also treat it as a geometric series because it is geometric. You're going to find out that the radius of convergence is 1. It's centered at 1, and therefore the interval is 0 to 2. Outside, for all negative numbers, for every number bigger than 2, this is not true. In fact, if you think about it, it's ridiculous. It couldn't possibly be true. But for every single x between 0 and 2, this series converges to that function. Okay, so we can't ignore it, the interval of convergence. Sometimes we luck out, it converges everywhere, and so we don't have to pay any attention. But sometimes it doesn't. And so we need to, once we find a Taylor series or Maclaurin series, we should immediately apply the ratio test to see where does it converge, what is the interval, the ratio of the radius of convergence. All right, so I mentioned I want to do an example to illustrate, especially these top two, how this whole thing works. The calculus professor did a little bit at the end, but we can do a little more graphic example. So I'm going to pause you while I change the board. Right back. All right, here is the first example. It follows up on the example from the previous video, the calculus professor. So we're going to look at the same function he did, sine of x. We're talking about the Maclaurin series. We're centering it at 0. And as discussed in that video, here is the Maclaurin series. I wrote it out term by term rather than in sigma form. So I want to show you, let you use your calculators to show you how this thing works. Okay, by picking these coefficients, all the even powered coefficients are 0. The sign doesn't need them. And then for the odd powers, it's just dividing by the corresponding factorial with the sign alternating. So get your calculators out, set them to radians. In case you just did physics and they're set to degrees. And then for the viewing window, let's let x's go from -4 to 4. And the y values from -2 to 2. Remember, we're trying to create a sine wave. So the sine wave exists between -1 and 1, but we'd like to see how these functions sort of find that sine wave. They'll come from above or below and connect with it for a little while. And then in your function part of your graphing calculator, build these 4 functions in, sine of x, and then we'll just gradually add terms from the Maclaurin series. The first term is the linear function that we can skip right over it. You can understand that from the video. But let's take the 3rd power and then the 5th power. So graph these one at a time. Actually, put them into your calculator as 4 separate functions. Or better, do the first 2. Put in y equals sine x, and then the second one, x minus x cubed over 3 factorial, and then graph those. And notice how, you're going to get a sine wave, of course, the first one, and then you're going to get a 3rd degree polynomial. I think it's going to come from above, and it's like a sine-seeking function. It's going to come down and connect with that sine function. And for a little while, around 0 in both directions, you're not going to be able to tell the functions apart. That is, those functions are, to the naked eye, identical for some interval of x values. And then, of course, the 3rd degree polynomial has to separate from it and head down to -infinity with a negative 3rd degree coefficient. All right, so you can kind of see, and then make a mental note on your calculator of where the 2 functions meet up. Like how much of your calculator screen can you really not tell them apart? And then go back to your function input screen and add the next term in, x to the 5th over 5 factorial, and graph those. So we're going to leave sine in there, and now to your second function, you already have this in there. We're just going to add that term at the end, x to the 5th over 5 factorial. And the same thing is going to happen. It's going to come, let's see, x to the 5th, the coefficient is positive, so it's going to come from below, and then at some point it's going to latch onto that sine function. And on your screen, you're not going to be able to tell them apart. For a further distance, x cubed, you can go out part way, x to the 5th, you can go out further. And eventually, of course, this 5th degree, it's going to shoot off to infinity. It says goodbye to the sine function and takes off. Okay, and now make a mental note of how much of your screen can you not tell them apart. It should be a bigger interval than happened for just the 3rd degree polynomial. And then we can do it again. You can do it forever because there's an infinite number of terms, but we can go back and add this next term in. You can find factorial on the probability menu, or you could just calculate it. 5 factorial is 120. You just want to punch the number in for these. 7 factorial, 120 times 6 is 720 times 7 is, I don't know. Calculate 7 factorial, or find the factorial button on your 5140. That's what I want to say. That may not be right. 14, 50, 40. Anyway, you know how to get 7 factorial one way or another. And so by picking our coefficients in this fashion, we can make this polynomial, these polynomials, look exactly like the graph of the sine wave. And because on the previous board we saw, I didn't see it, but I told you, it converges everywhere. So if we keep on going, we can make those functions identical for all x values. We have to go to infinity. All right, I want to do one more example. And so let me pause you while I set it. All right, the second example is for e to the x. Remember on the last example, we could, by choosing our coefficients carefully, we could create a Taylor series that became identical to the sine wave, this back and forth behavior. Now I want to show you how we can, by just changing the coefficients, we can now create a power series that has the graph of the e to the x, exponential growth. Okay, so there's our function, and there is the Maclaurin series for it. I talked through why that is the case. We didn't actually work out the details. The calculus professor works out the details for e to the minus x in one of the problems he chose. So you can see how that works. And this is simpler because it's just e to the x. And I told you earlier, it converges for all x. We'll just believe that. You can use the ratio test to prove it. So what I want you to do now is clear out your function screens on your calculator. I didn't tell you the window. We don't care about radians or degrees on this example. So let's let x go from, I don't know, -3 to 3. And let's let y go from -1 to, I don't know, start with 5. And you can adjust that if you need to. Unlike sine, the exponential, it's not trapped between two values. It heads off to infinity. And I include -1 here just so we can see how those polynomials maybe find the curve, and then you can see it come up. If it comes up from below, we can just graph them and figure out. All right, and then in your calculator, you punch in e to the x, and then if you want the linear, the first degree polynomial, then we'll just take the first two terms, 1 plus x. And of course, that's a line, and you can see how the line approximates e to the x for a little while, not very far. It's not very good, although one of my colleagues here at George Fox in past years was a physical chemist, and his research had him working with molecular distances super tiny, close to 0, and he used the exponential function. And for his work, remember, the Maclaurin series, we're centering it at 0. So from 0 up or down some distance, these polynomials ought to be good approximators. And for his work, he just always treated e to the x was 1 plus x. His values of x were so small that all he needed was the first two terms. And I think maybe it's easy in physical chemistry to maybe think those are the same thing. And they're not quite. I mean, they're really, really close if x is super close to 0. You can see on your calculators. But to move out the exponential behavior further, we need to add more terms in. So I've added the quadratic term, the second degree. Of course, 2 factorial is 2, so I did the work there. And then finally, notice I skipped the third degree just because let's add 2 more just for the fun of it. And so here's the 4th degree Taylor polynomial. And graph them on your calculator and see, how far away from 0 do these various functions look like an exponential curve. Now, the last example, we showed how we can modify the coefficients to make it look like a sine wave. And now we're showing how we can modify them to make it look like an exponential growth wave. So you can see there's a great deal of flexibility in how we choose those coefficients. We can make any shape we want. It's sort of like, we're sculptors and we're sculpting these coefficients so that the corresponding polynomials have the shape that we want them to have. And by the way, I don't think I remember seeing this in the calculus professor's video. I'll try to get some homework. He talked about the Taylor, the Maclaurin series. The series implies infinity. It goes on and on and on. If I stop short of infinity, like we did here, only up to the first power, second power, fourth power, these guys are called Taylor slash Maclaurin polynomials. So there's a good chance I'll assign a problem in the homework where you're asked to find the third degree polynomial for third degree Taylor polynomial or Maclaurin polynomial for some function. And then what you want to do is run it up to the third power. And then you're done if you're looking for a polynomial. So polynomial, a finite number of terms, whereas the series, we find the pattern that goes on and on and on forever. Let me say one last thing, and the calculus professor hinted at this. Taylor and Maclaurin lived 200 years ago, probably a little bit more than that. And of course, back then, calculating was difficult, especially with what we call transcendental functions, trig functions, log functions, exponentials, and so on. And so a lot of mathematics was generated to help people do calculations. And that's exactly what I believe, what motivated Taylor and Maclaurin. That is, if we don't have a super nice angle, a sine function, like how does it get its value? We don't know. I mean, we hit a button on our calculator and boom, a value jumps out. But how did they do it with no calculator? Well, they figured out how they could write those kinds of functions as polynomials. And then it's just simple arithmetic, right? Adding and subtracting. That's all you do in a polynomial. So that was what motivated originally, just to help them do calculations. But over the years, people have found lots and lots of other uses for these power series, Taylor and Maclaurin power series, and therefore they're part of our calculus literature today, not so we can do calculations. If we need to know the sine of 2.78 radians, we just ask our calculator. We never plug it in to some Taylor polynomial. But there are, like I said, people have found other uses for these functions that have nothing to do with calculation. And so any person, educated in the engineering, math, science disciplines really need to know, the nature of Taylor and Maclaurin series. And this one right here, the one for e to the x, the most important one. I didn't bring my book in with me, but towards the end of section 3, chapter 11, section 3, there is a summary of the most commonly used. I believe they are all Maclaurin series. They're all, that's probably not true. Most of them are, maybe not all, but Maclaurin / Taylor series. They show you the series. Maybe they write it out long form like this. Maybe they write it in sigma form. I really don't remember. Maybe they do both. They also will show you the interval of convergence, which is a very important thing to know as well. Because outside that interval, it's garbage. There's no meaning whatsoever. We luck out for e to the x and sine x. It's also true for cosine x that they converge everywhere, so we can be super careless about the x values. And when you look at that page, the summary in chapter 11, section 3, look at the difference between sine and cosine. It should make a really super good sense to you when you see it. Remember sine worked out on the calculus professor's video and talked about earlier here. hits only the odd powers. And guess what? The cosine is only going to hit the even powers. So all the odd coefficients will turn out to be 0. But anyway, you can look that up, and hopefully the homework will direct you to some of these things. All right, that's it. I'll post the homework, the next one, sometime on Friday. Talk to you later.